Good. Is that one all right?
Wait, could you do the arrow pushing for me, please?
For the whole thing?
Yeah.
Yeah, absolutely. Okay. Nucleophile. Lone pair on the oxygen acts as our nucleophile. We attack the carbonyl carbon. Electrons go up to the oxygen. We generate our tetrahedral intermediate. So we have O minus. We have water that just added in. And we have chlorine. Okay? We have, so some people will say, like, why do we collapse back down the tetrahedral intermediate when I have 3 sigma bonds or have actually 4 sigma bonds on this carbon? And it's because I have right now 3 electronegative atoms attached to the same carbon, not stable, okay? So the oxygen with the minus charge is going to use one of the lone pairs and form a pi bond, reform the pi bond. Now we're going to kick off a leaving group. I have 2 leaving groups here, right? I can kick back off water, and that just takes me back to where I was. Or I can kick off chlorine, and that gets to my first intermediate. Okay? Okay. We can favor water staying on the molecule by swamping this with water. We can use the Le Chatelier's principle, okay? So we're at this intermediate, and we have other water molecules floating around. Usually you run this reaction in water, and water, or chlorine if you prefer, will pull off one of the protons so that we can give that oxygen back its second pair of electrons and allow it to be more stable. Good? All right, so we did addition. This is the addition step. And then we did the this is the addition step. This is the elimination step. Good? Okay. Next one, we have an anhydride. What's the leaving group on the anhydride? Well, it is going to be everything that's attached to the carbonyl. Okay. It just happens to be an acetate or an acetate derivative here. So that's my leaving group. That's the leaving group. And the nucleophile is going to be the oxygen of my alcohol. Okay? So I'm going to do a substitution of my nucleophile in place of my leaving group. And first I'm going to draw my starting material minus my leaving group. New bond is between the carbonyl carbon and the oxygen of my nucleophile. At first, that oxygen has the ethyl group and a proton that came along for the ride. Okay. Which, just like before, we're going to just remove that proton to make it into a stable product. Okay. So far we've looked at the acid chloride and the anhydride. Both of those really good leaving groups. So we haven't had to really add anything to help this go. Any questions about these so far? So good? Okay. This is another way that you can be asked the reaction, which is, what did I add in here? What was the reagent that this acid chloride reacted with to make the amide? Okay? So if you zoom in on what's changed, there's my leaving group. This is what's in its place. Okay? So, do I have a good leaving group? I have a fabulous leaving group. So this is a good leaving group. Okay? I'm not going to need to add anything else in to help this reaction go. I can if I want to, but it's overkill. All right? So what do I need to bring in as a reagent? Describe it to me. Yeah,
Is it the H2N methyl?
good. So the nitrogen, so this is what we see that's attached in the product, right? Nitrogen has 3 bonds, so the third one would be a proton that we would remove in the process. Just like we did right above, where the alcohol came in with a proton that gets removed, the nitrogen would come in with an extra proton. You don't need to draw it out. You can write it if you want to. If you were to write this out, it would just be H2NMe. Okay. Is it wrong if you write H plus? Nope. Is it wrong if you put heat? Nope. Just overkill. Just don't need it. Was that your question? Oh, yeah.
I was gonna ask if we need to write if there's excess, or we just assume.
So for now, assume that there's excess unless we specify one equivalent.
Okay.
Yeah, you can assume excess. Good. All right. Let's take a look at this one. All right, we start off, we have an ester, and we are generating an ester. All right, so we're doing a transformation that's going to basically have pretty equal energy. All right, but we also know that our leaving group is this methoxy group. Not a great leaving group, so we probably need to add in some assistance to get it to leave. So you can do this in 2 ways. We can either add a base to help it, or we can add an acid to help it. So what does the nucleophile look like? Can you visualize what it looks like? So the nucleophile is what has replaced the leaving group, which is the phenoxy group here. All right, now, you may say, but there's still an oxygen, there was an oxygen before, how do I know that that's not the same oxygen? You can do this multiple ways. You can go through a method that stays as the same oxygen. The only way you can do that is if this becomes a carboxylic acid from which you then make a new ester, okay? If you want to keep that oxygen there. However, if we treat this whole thing as the leaving group, which I recommend, versus just the methyl group as the leaving group, we have a lot more tools to use. Okay, does that make sense? All right, so if you tried to make the methyl group into a leaving group, it's not wrong. There's just some other things you would need to do. It's not easy. All right, so what does our nucleophile have to have? Yeah?
Oxygen and phenol.
Yeah, it has to have the oxygen and the phenyl. So if we are going to add acid in, then this is going to be a neutral alcohol. And then we add H plus. Okay. We don't want to add H3O plus because we're adding water then, which is a competing nucleophile. Okay. So if you're curious as far as like, well, what would you add then? You would probably add a drop of sulfuric acid or something that does not compete. All right, just no water. Or you can add a base catalyst. If you want to add a base catalyst, what you want to do is add in a little bit of the phenoxide as a strong nucleophile. Okay. And it's not going to be in a bottle with a minus charge. You pick your favorite cation, maybe it's sodium, maybe it's potassium, and some alcohol. Does that make sense? Any questions about that? No? Okay. This one looks a little different. Okay? And that's because the 2 ends of our carboxylic acid derivative are attached. Okay? Don't treat this any differently. All right, so we have an anhydride. What's the leaving group? Well, we're going to pick one carbonyl as the carbonyl that's going to undergo the change. All right, you'll notice that this is a symmetric molecule. So it doesn't matter if I have the nucleophile attack this one or if I have the nucleophile attack this one. It's going to give me the same product, okay? And I would say 99.9 times the anhydride that you start with is a symmetric anhydride for that reason, okay? So pick whichever carbonyl you want to be the electrophile. I'm going to pick this one, which means that this is my leaving group. This is the leaving group. Okay? Forget that it's attached to the other carbonyl through the chain. It's the leaving group. It's going to leave that carbonyl carbon. Okay? What's my nucleophile? Oxygen. So oxygen is going to be my nucleophile. It is going to bring with it the methyl group, and I highlighted, but you can't see it. It is going to bring with it the hydrogen and the methyl group. So let's take a look at what this looks like. So I have a ring, 1, 2, 3, 4 carbons big. Okay. This might be worth doing the arrow pushing for this one. What do you think? Yeah? Okay. So we're going to attack carbon 1 with our nucleophile. Lone pair on the oxygen is going to attack carbon 1. Electrons go up to the oxygen. We're going to make our tetrahedral intermediate. So I still have my 5-membered ring. Carbon 4 still has a carbonyl. Now at carbon 1, I have a single bond to O minus and a single bond to the oxygen in methanol. And that has a plus charge on it because the oxygen has 3 bonds. Okay. Very quickly, this is going to collapse. We did the addition, now we're going to do the elimination. Why? Because that carbon right now has 3 oxygens attached to it. Very unstable. All right. Lone pair is going to collapse back down, and it's going to kick off a leaving group. Could it kick off methanol? Yep. That's going to take us back to where we started. Okay? But if we put in a lot of methanol, we're going to push the reaction forward, and that's going to kick off our leaving group. And I'm going to color in this oxygen as pink just so that we can kind of follow it. All right, so what I've done right now is I broke the bond between carbon 1 and that pink oxygen. Okay, so I'm going to draw this next product or this next intermediate kind of ugly because I want to try to keep all the atoms where they are just for clarity purposes. So I've reformed the carbonyl at carbon 1. It's still attached, still attached to 2, attached to 3, attached to 4. 4 still has a double bond to an oxygen and a single bond to the pink oxygen. And that oxygen has a minus charge. And carbon 1 has the new bond to oxygen. And that oxygen still has a CH3 group and a proton attached. Okay, so it's not pretty, but at least we kept kind of the atoms where they were before. All right, this does not look very stable. What do you think is going to happen really quickly? Yeah, what do you think? Was that volunteering?
Maybe the hydrogen.
Close. I'm going to change your words though. Proton transfer. So instead of moving H minus, we're going to move H plus. Okay? So you can imagine very quickly that we have this negatively charged oxygen that might grab that proton to neutralize over there. Could this happen right here before the leaving group left? Sure. I don't know when it's going to happen, but it's going to happen pretty quickly. And what that does is neutralizes our product. So we end up with an ester at carbon 1 and a carboxylic acid on carbon 4. Okay. And that's our first product that we get out. Good? I feel like there are question marks with that one. Okay. You can draw it like this. This is perfectly acceptable. If you want to draw it as a straight zigzag chain, you can do that too. It would look like this if you drew it that way. So let's see, it's 4, 3, 2, 1. Good? How do we feel about these? Yes?
If we write it like the top one,
Yeah.
it'll be correct.
Absolutely. Yep. Absolutely. Yes.
Sorry, I'm kind of still confused. Because the living group that you highlighted on the yellow parts for the first product is acid product, right? And because acid is irrelevant, it still stays in the finishing product. You know, like the
Which carbonyl are we talking about?
the one highlighted in yellow.
Oh, this one right here? Yeah, so that stays as a carbonyl this whole time. So we have here, 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 which is there.
Why is that leaving?
Why is it a leaving group?
Okay, I understand.
So this is an anhydride. So generally speaking, the anhydride has this acetate as a leaving group, okay? This case just happens to have these two groups connected. So this is still a leaving group. It left that carbon. So the group left carbon 1. It just happens to be tethered through carbon 2 and 3 to the other side of the molecule.
So in a situation where it's not tethered, do we expect that same chemical to stay?
No, if it wasn't tethered, it would form a completely new molecule. Yep, great question. Does that make sense? We're going to do some things with tethered stuff maybe today. All right, I know that was a quick and dirty review of the carboxylic acids. Do you feel a little bit more confident with them? Yeah? Okay. So what we're going to do now is jump to some new chemistry. Yeah. Don't be all too excited. All right, so we are going to go, let me see, 206, guided notes 3. So we are in guided notes 3. So this group of reactions that we're getting ready to talk about are called condensation or alpha condensation reactions. I call them alpha substitution reactions because condensation is kind of like, what does that mean? Okay, so what we're going to be doing is we're going to be doing substitutions on the alpha carbon. Okay, we're going to be substituting a hydrogen that was there with something else. So we're going to be removing a hydrogen and we're going to add whatever the electrophile is going to be. Okay, so up until now, what we've been doing is we've been looking at carbonyls, whether it be aldehydes or ketones or carboxylic acid derivatives, and we're like, okay, I know that I have a delta minus on the oxygen, I have a delta plus on the carbon, okay? Which means that if I have a nucleophile, it's gonna add to the carbon, okay? The oxygen can act as a nucleophile itself, and it can do things like grab a hold of protons or other electrophiles. Okay, right? We've seen that like a million times now. Now we're going to talk about something that's different, a different type of reactivity that these can do. What we're going to do now is we are going to talk about how this alpha carbon can act as a nucleophile. Okay, so how does it act as a nucleophile? Well, this position is really acidic, relatively speaking, which means that we're going to be able to remove a proton from that position and generate a nucleophile. which is the conjugate base of that aldehyde or ketone, or ester or amide. We're going to focus mostly on aldehydes and ketones. Okay. So the overall transformation is going to look like this. We are going to remove what is called the alpha proton. This is the alpha proton. It's a proton on the alpha carbon. So the alpha carbon, to remind you, is the one that's next to the carbonyl. This is the alpha carbon. Okay, so we're going to remove the proton, and that's going to generate a nucleophile. So when we remove the proton, we're going to generate a nucleophile. Okay, that nucleophile will then attack an electrophile. And we'll make a new bond between the alpha carbon and that electrophile. Okay? Now, I'm not going to lie to you. These are harder to visualize. Why? Because we don't draw in hydrogens. Okay? Up until now, we've been like exchanging an OH group for an NR2 group or something that's visually we can see it happening for the most part. Okay? Now we're going to be exchanging something we don't draw in for something new, and it's harder to visualize. So just kind of prepare yourself for that, and that will definitely help you if you understand that this is happening. Okay, so we're going to talk about, first of all, why we can do that, why we can pull this random proton off the alpha position. Generally speaking, sp3 hybridized carbons are not acidic. Do you guys know what the pK is of an sp3, like an ethyl group? What pK is? Range-ish? 20? Keep going. What'd you say? 50. 50. Okay? That is really, really high. Does anybody know what water is? 15.7, okay? So that means that typically an sp3 hybridized carbon is 10 to the 34.3 times less acidic. That is a crap load less acidic, right? So why does it work in this case? And we're going to spend some time talking about it. So one of the big things that's going to lead to this acidity is the fact that this anion is stabilized through resonance. Okay, resonance is coming back with a force right now. All right, so if you feel uncomfortable with resonance, please come and let's chat. Specifically with negative charges next to double bonds. Okay, we're going to cover it a little bit today, but please let me know. So there's a resonance form where this negative charge, these electrons can delocalize. They can form a pi bond between those two carbons such that the adjacent pi bond gets pushed up to the oxygen. Okay, and that will give us the structure here. Okay, so we have resonance stabilization of this conjugate base once we remove the alpha proton, which leads it to be more acidic. This is a structure called the enolate. Okay. You were first introduced to a version of the enolate called the enol back in 2005. Okay. You guys remember that? The enol? If you had Downing, you may have done a puppet show, the en and the all coming together. Okay. So this is a very, very important functional group in not only synthetic chemistry, but also biological chemistry. You have enzymes called enolases, and their whole job is to make this happen and to make this nucleophile so that it can do other things, okay? Very important class of reactions. Anybody planning on taking biochem? Yeah, a lot of you are, okay? You're gonna see this functional group over and over and over again. Okay, so back in 205, we introduced a term called tautomerization. I hope you heard that before, okay? And what tautomerization, if you didn't, not a big deal, I'm gonna reintroduce it now. What tautomerization is, it's a rearrangement reaction. It's a rearrangement reaction. Okay, that exists between two different forms. One is what's called the keto form, where we have a carbonyl. Oh, sorry, not ketone, keto. Okay. It is in equilibrium with the enol form. So enol means that we have an OH group plus an alkene, and they're attached. So an alcohol, which is where the all comes from, and the ene from the alkene gives you enol. Together, this pair are called the tautomers. Tautomers. So a tautomerization is going to go back and forth between the two tautomers. Okay? So tautomers, they're just isomers. Isomers, constitutional isomers, structural isomers. And if you have anything around that can act as an acid or a base, it will facilitate the conversion from one to the other, okay? That could be hydroxide, it could be a proton, it could be an acidic side chain of an amino acid that can act as a temporary proton donor. That's how your enolases are gonna work, okay? But they're gonna tautomerize between the two. So we're gonna go through the arrow pushing for that tautomerization. They're very short. Okay, and then we're going to talk about where does this equilibrium sit and how can we push it to one side or the other, and then use the enol or the enolate. Okay, so if we have an acid catalyzed tautomerization, so we have something around that's going to act as an acid, we can go back and forth between the two forms. We have our keto form that will form the enol, and then that enol form can go back to the keto form. Okay. So rather than try to superimpose two arrow pushings on the same one, I've just split this up. So this is going to be, this is the forward reaction, and this is kind of like the reverse, if you want to think of it that way. Okay. So we have a carbonyl and we have an acid around. Generally speaking, up until now, and we're not going to change anything, what would happen if you have a carbonyl and you have acid around? One thing that could be helpful is to remember this is delta plus and this is delta minus. Yeah?
The oxygen grab the hydrogen.
Perfect. Lone pair on oxygen is going to grab the proton, which kicks off the conjugate base of our acid. Okay, so what just happened was just that we protonated. And in acid or acidic solution, these protons are coming on and off and on and off and on and off. Okay? This has a resonance form. Right now I have a positive charge on the oxygen. There's a resonance form where that oxygen says, I'm the second most electronegative atom. I am not going to have the positive charge here. So the oxygen pulls the pi electrons back to itself, which results in the formation of a carbocation. These are resonance forms, so we have an average of these two in reality. Okay? Good? Well, that carbon's like, I don't have a full octet if the oxygen takes the electrons away, but if I pull electrons from the neighboring carbon, I can form a pi bond. And the only way you can do that is if something acts as our base, like the conjugate base of our acid, comes along, pulls off that proton so that the electrons can come down to form the double bond. That's just an E1 reaction right there. Carbocation formed, pulled off the adjacent proton, electrons come down, make the pi bond. Okay, not a big deal. There are ways that you can draw this shorter. You can combine these two steps, okay? But this way you can see the driving force for all of it. Okay, so the keto form went to the enol. Enol can go backwards. We're gonna do the same thing in reverse. Last thing we did was we formed the double bond and we removed the proton. We go backwards. We're going to break the double bond and grab the proton back. So going backwards, pi bond grabs the proton, and we reversibly reprotonate. The proton is going to go to the carbon, not the carbon with the oxygen, but the other carbon. The carbon with the oxygen becomes the carbocation. It's the most substituted, and it is stabilized with resonance. Okay, so lone pair on the oxygen gets attracted to that positive charge. The oxygen starts sharing, and we have a resonance form where that double bond has reformed. And that oxygen has a positive charge, which we know it doesn't like. So it yells at the conjugate base to come and grab a hold of the proton so that the oxygen can get that second lone pair back. And that gets us back to our keto form. Like little arrows. Okay, does that make sense? Okay. So in this step, or in this set of catalyzed reactions, we have positive charges, right? Positive charges either on the oxygen or the carbon. And that's driving the reaction to go either towards the keto form or the enol form. And it's going to go back and forth until there's an equilibrium established. Okay, we'll talk about that a little bit more. Any questions on that? It's not so bad, right? Okay. So in the base catalyzed reaction, want to stress we're under basic catalyzed reactions or base catalyzed reaction, which means there's going to be no positive charges. Okay, no positive charges when you have a base around. Lily is so stressed out right now. I just thought I'd tell you that. She's like flat out, like done. Okay. Okay, so no positive charges. We're not protonating anything. We're not making carbocations. No positive charges, okay? So once again, I'm going to have some kind of a catalytic base around, something that has a nice negative charge on it. And it's going to react, delta plus on the carbon, delta minus on the oxygen. It's going to react with the keto form. So let me go ahead and label again. This is keto going to enol. And then we're going to look at the reverse, which is the enol going back to the keto. Okay? So up until now, what we've done is we've said, nucleophile. It's going to attack my carbonyl carbon, electrons go to the oxygen. That's still happening, but something else is going to happen now. And that is because of the resonance form. Resonance form has the lone pair localized up on the oxygen. Okay? I know you're going to say, Nolan, you just said there's no carbocation, right? This is not really a carbocation because it's more of a zwitterion. Do you guys know that term? Where we have a minus and a positive together. It's not a full positive carbocation like we had like right there, okay? This is a zwitterion. So overall, still neutral, not positively charged, okay? So now what's gonna happen is that base is gonna pull off the alpha proton, Electrons are going to flow down to form the pi bond. And that is going to give us our enolate. So this is the enolate. Okay, I'm sorry, let me put color on those arrows there, and there. Okay. Which then is going to need to be protonated. So we have now the conjugate acid of the base. That can be the proton donor. So oxygen can grab the proton, and that regenerates our base. Okay. You'll notice that this is really similar to what we did under the acid catalyzed conditions. Okay. Acid catalyzed, you protonate first, then you remove the proton. Okay. Acid catalyzed, we protonate first, then we remove the alpha proton. Base catalyzed, remove the alpha proton, and then we protonate. Just opposite steps. Okay? All right, if we want to go backwards, we're going to do the opposite. We're going to pull off the proton from the oxygen first. That's going to make our enolate. Okay. That has a resonance form where a pair of the electrons from the oxygen are going to come down to form the pi bond, which breaks the adjacent pi bond, and those electrons go to the alpha carbon. And that gives, that gives us a different version of our enolate, which then is going to react with the conjugate acid of our base as the source of the hydrogen or the proton. Okay? So we have back and forth with acid catalyzed, and we have back and forth with base catalyzed. Good? Okay. This is how it happens in biology too. You have some amino acids that have a proton on them in biological pH. Some of the side chains, they're going to act under acid catalyzed conditions. Some of your amino acids have a negative charge on the side chain. They're going to react like base catalyzed reactions. Okay? So learning it this way, like we're doing in orgo, is kind of the simplified version in that we don't have a huge protein structure, which is what you're going to grow towards. Okay? Does that make sense? Awesome. Any questions? You will have to do one of these 4 on the exam. Okay? You'll see one of them on the practice exam. Okay? So you'll go either keto to enol or enol to keto, and you'll be either under basic or acidic conditions. Good? All right. Okay, so let's talk about equilibrium. I always find that when I get to this point, and even when I was learning, I was like, how am I supposed to know what's happening? I have carbonyl carbons that things can be adding to. I have alpha protons that things can be coming up from. And to be honest with you, all of these things are going to be happening at the same time. So we need to kind of have an understanding of kind of where we are when we have an acid or a base around, number-wise, to kind of think about moving forward. So here we have your aldehyde. So here's your aldehyde. And here's your ketone. And their corresponding enols, and we're at equilibrium. So here's the keto form, and here's the enol form. Okay? So when we think about equilibrium, we think about like the energy difference between the two, right? Is that what you guys think about when you think about equilibrium? You think about like how much do I have of each? And that's going to be dictated by what the relative energy of the two are. So I'm going to give you some numbers here. Generally speaking, for this aldehyde, the delta G for this equilibrium, don't have to memorize numbers. This delta G is plus 8.5, sorry, this is in kilocals, kilocal per mole. I have to update my notes to put them in kilojoules. Okay? What side is favored? The keto or the enol? Okay. If it's hard for you to visualize, let's just draw the reaction coordinate diagram. We have our G is our energy, and if I put the aldehyde here, where's the enol relative? Higher or lower? Higher, right? So here's the enol form. Okay, and the difference in energy here, that's your delta G. Well, I was about to write A there. Delta G. Okay, so now that we drew it out, like on an energy diagram, is it easier for you to have a feeling for which side's favored? Yeah? Which side's favored? The keto form, right? And this is true whether or not it's an aldehyde, a ketone, the left side, yeah, the keto form. The aldehyde, the ketone, the ester, the amide, it doesn't matter which functional group you're talking about. The keto form is always favored. So we have the keto versus the enol. Okay, the keto is always favored. Keto, always, as far as I know, favored. That's my disclosure. Okay? So if I give you here now the number for the delta G for the ketone between its keto and enol form, the delta G here is plus 11.3 kilocals per mole. Okay. So what does that mean? Is that more favored or less favored than the enol of the aldehyde? It's even less favored, right? So just to kind of tie some things together here, our delta G is tied directly to how much of each we have, right? So the equation that tells us that, does anybody know off the top of their head? Okay, good one to know. Minus RT ln of KEQ. Okay. What's KEQ? KEQ is a ratio, right? What's on the top? Products over reactants, right? KEQ is our equilibrium constant. Sorry, not constant. Equilibrium constant, where we have the concentration of the products over the concentration of the reactants. Okay, in this case, that means that we have the concentration of the enol over the concentration of the keto. Okay, so if I plug in the delta G's that I have above, and I plug in R, which is the gas constant, and let's say it's at room temperature, what we find is that for the aldehyde, so for the aldehyde, delta G for the aldehyde, it's going to give us a KEQ equal to 6 times 10 to the minus 7th. You ever look at numbers like this and go, okay, great, what does that mean? I do. That doesn't mean anything to me really until I say that is the same as saying for every 6 enol forms, I have 10 million keto forms. Does that mean more to you? It means a heck of a lot more to me, okay? For the ketone, the KEQ is even worse. It's 5 times 10 to the minus ninth. I didn't write out that fraction, but we're dealing with, I think, the billion area, like something per billion. Okay? So we don't have a lot. That's a big way of saying we're making, or when the equilibrium is established, we have lots of this, and we have a tiny amount of this. All right? So that means that the ketone is not always going to be in the enol form. It's around, it's doing additional elimination reactions, it's doing addition, it's doing all of these things in equilibrium. Yay for us. Okay, so that means that, oh, look, I did that down here. This is just duplicate, see above. Okay, so that just means that we can't rely on equilibrium for these reactions, these substitutions at the alpha position to do anything. We're going to need to force these reactions to happen. Okay, so any questions on that? I'm not going to ask you for these numbers, but I just wanted to drive home the point that we have very little enol naturally. Okay? All right, so let's talk about the acidity of these alpha protons. It did not like to give me that in this program. So let's talk about the acidity of these alpha protons. So we said a minute ago that a regular sp3 hybridized carbon has a pKa around 50, okay? Our pKa scale only really goes up to 14, so we have to extrapolate beyond that, okay? Does anybody know what the pKa of an alcohol is around? We're talking about water. It's pretty close to water. About, what'd you say? It's usually between 15 and 18, depending on what the R group is. So I'm just going to say this is a pKa of about 17. Okay, just to kind of pick a spot in the middle. Okay. Anybody want to take a guess what the pKa is of the alpha proton? You could pick any number that you wanted to right now. Well, it's going to be more acidic than an sp3 hybridized carbon because the conjugate base is resonance stabilized. Do you think it's going to be as low as the proton in alcohol? Some of them are. Isn't that crazy? So depending on what this group is, this alpha proton can be anywhere between 16 and, where are we going to go? We're going to go up to 30. Okay? Why is that? Because once again, if we react this with a base, and the base removes that alpha proton, we generate an enolate that is stabilized through resonance. Okay? So in resonance, that lone pair will delocalize in between the two carbons, which breaks the adjacent pi bond, and the electrons go up to the oxygen. Okay? So we delocalize those electrons. So the conjugate base is resonance stabilized, which makes the acid from which it came more acidic than typical. Okay. So unfortunately, I need you to memorize a few. There are 1, 2, 3, 4, 5, 6, 7, 8. Only 8. Okay? 3 of them have a pattern to them that I'll tell you about. Okay. So we have 5 carbonyls that we're going to focus on. We have, these are our acid halides, aldehydes, ketones, esters, and amides. okay? The pKs are going to track with their reactivity, okay? So if you remember, like acid chlorides are more reactive than than an aldehyde, which are more reactive than an ester, which are more reactive than the amide. It tracks here, okay? So pK for an acid chloride or an acid bromide is going to be about 16. And what we're talking about is the proton at this position. So for all of these, we're going to be talking about the proton that's attached to the alpha carbon. Okay. So for all of these, we're going to jump up about 5, which is a nice way to remember it. Okay, about 5. Okay, aldehydes, they're going to be about 19. Ketones about 20. Okay, if you said 20 for an aldehyde, that's fine, because depending on what the R groups that are attached to them, it's going to vary a little bit. Generally, 2 pKs, 3 pKs units are acceptable. We're going to jump 5, we get to an ester, we're up around 25. Okay, we get to an amide, and this is going to be the least acidic at 30. Okay. All right, then we have a class of the dicarbonyls. Dicarbonyls have at least one and maybe multiple alpha carbons, but the one we're going to focus on is the one between the 2 carbonyls and the protons that are attached to that. Do you think that these are more or less acidic than the monocarbonyls? If I pull off a proton from, let's say if I pull off this proton, I generate a conjugate base that looks like this. What can stabilize it? Resonance. Which direction are you going to resonate? Both. Either. Both. This has more resonance to help stabilize it. So we can resonate in this direction, we can resonate in that direction. So it has 2 times the resonance. Resonance. Sorry, running out of room. Resonance. Okay, so is that more stable than the conjugate base of, let's say, this? Yeah, it's a lot more stable. Okay, so does that mean that the dicarbonyl acid is going to be more or less acidic than the mono? We're making a more stable conjugate base, so they're going to be more acidic. Good. Okay. So pKa between 2 ketones or 2 aldehydes is 9. That's like ammonium, right? NH4 plus. It's like down in that range. Like way more acidic than an alcohol. So these go from either dialdehyde, diketone, or ketoaldehyde to 1 aldehyde with a ester or between 2 esters. And this rule is called the 9, 11, 13. So they go up 2 each time. 9, 11, 13. Okay. So these 8 you're going to need to know. Okay. All right. So I want to talk about forming the enolates from these carbonyls. So we need to talk about the fact that we're going to be forming an equilibrium where we have a base that can pull off this alpha proton, Electrons go to the carbonyl, or actually I'll have them resonate all the way up. Electrons between the carbon and the hydrogen are going to resonate back and forth between the carbon and the oxygen. Okay, this is an equilibrium, depending on what our base is. Okay, so this is our acid, this is our base, this is our conjugate acid, this is our conjugate base. So where this equilibrium will fall depends on the base you use. Okay, so where equilibrium falls, meaning does it favor the right or does it favor the left, depends on the base used. Okay. If we want to highly favor the enolate, the right-hand side, how can I, because this proton acidity, the strength of this acid is set by whatever our molecule is. How can I push this reaction to the right? What type of base do I want to use then? Strong base, weak base? If I want to drive the equilibrium in this direction to the right, I need to use a super strong base, okay? So to favor the right, we're going to need favor enolate. We need to form using a strong base, okay? So what we're going to do next time is talk about what those bases are and what happens if we use a weaker base. And then we're going to jump into our first reactions. There's a little bit of what we're going to do on Tuesday on the exam, but it is maybe like 4 to 5% of what's on the exam, okay? And you'll recognize on the practice exam if we haven't gotten to that yet, okay? Cool? All right, so once again, on the back table is your pet molecule answer form or answer sheet, the project itself, and the practice exam. I will be posting all the PDF versions of that online as well. They're not up yet. Good morning, Lily. I will have your homework graded. Remember, I will grade it, but you get 100% for turning it in. But I'll post the answer key for that as well. What else? I will post your reagent list and reaction list as well. And if there's anything I'm forgetting, let me know. Yes?
The sample exam, are we supposed to turn it in?
No, that you don't turn in the sample exam. That's just for you.